Hello, welcome back to three-phase circuit analysis. Here what we're going to do is finally talk about the extremely important topic of power calculations in three-phase circuits. So we've done a lot of background theory. We've talked about magnetizing VARs, real and reactive power. We've done a review of power, and we've applied it to the three-phase circuits where we're sometimes trying to calculate the power using the line quantities, using the phase quantities. And if you're like me, or maybe not, who knows, but if you're like me, you get confused by so many different equations being thrown at you. But what I want to do in this section is obviously work the first problem, but I also want to kind of cut through all of that confusion and show you that really when you're introduced to all of these things and you have so many different equations to work with, really what's happening is we've derived different relations that can be used in different cases. I want you to think back to basic power analysis that you learned long time ago with a resistor, right? No capacitors or anything, just a resistor. What did you learn? You learned I squared R, P is equal to I squared R, right? And then you learned P is equal to V squared, the voltage drop across that resistor, V squared over R, right? And then you also learned that if you know the voltage and the current, the voltage across that resistor and the current through it, you can do I times V. Now I ask you, which one of those is best? And you say, well, none of them are best. They're all just different ways of doing it. That's exactly what you need to kind of realize for three-phase power calculations, right? So sometimes you use I times V because you know the current and the voltage going across an element, or the current flowing through an element. Sometimes you use V squared over R because you know the voltage and you know the resistance. And sometimes you do I squared R because you know the current and the resistance. If you do them all different ways, you're going to get the same answer, and which one you use just basically depends upon the problem you have. So that's all of these lessons we've done with, here's what you do for this power, here's the complex power, here's the power triangle, here's power factor, here's reactive factor. They're all just different ways of looking at the same thing because you're going to be given different things in your problem statement. So what I have done, this is the problem, we're going to get to the problem in just a second, but what I've done before we actually go into the problem is I have written down kind of a summary sheet over here. I'm going to try to leave this up unless I run out of room. And this is basically a summary of the most important power calculations or power results in all of the previous probably 3 or 4 lessons that we've talked about in one place. And so I want to go through it with you really quickly, even though I know you know most of the stuff or all of the stuff already because we've already covered it. Nothing here is new. So the first thing is, you know that complex power in any element or any impedance is going to consist of P plus JQ. P is the real part, Q is the imaginary part. So anytime you talk about reactive power, you're talking about the Q part. Anytime you're talking about real power, or sometimes we'll call it average power, we're talking about the P part, the real part. Now this complex power consists of P plus JQ, but it can be calculated multiple different ways, just like the resistor example, right? So here you have VI conjugate. Now notice the effectives under here, everywhere. This means these are RMS values. If you're using the amplitude of the wave, the tippy top, of the crest, then they're going to have other factors out here. But in power calculations, we always use the RMS value. So when you see effective everywhere, some books will say RMS, some books will say effective. But anyway, this value here, the voltage here, that's not the peak, that's the RMS value, which means you're basically divided by square root of 2. So anyway, you can calculate this complex power through any impedance by knowing the voltage across it and the power through it, so VI conjugate. That's what I've been telling you over and over again. But if you don't know the voltage, maybe you know the current and you know the impedance, then it's I squared Z. This is just like I squared R from regular power calculations. But if you don't know the current, maybe you just know the voltage and the impedance, then it's V squared magnitude, obviously, over Z. So the magnitude bars are because you usually know the current as a phasor quantity. So you want the magnitude, what sits out in front of that angle. That's what you put in here and you square it, times Z. That's what you put in here, the magnitude of the RMS value of the voltage squared divided by Z. But notice in this case, it's not just divided by Z, it's divided by Z conjugate. So you have to take another conjugate down there. We've derived all those before, but these are probably the most important things. In most of the problems here, I'm simply just going to use these equations. But the book, because we're dealing with three-phase power, they derive all kinds of other equations to throw at you to let you know, hey, there's other ways of doing it depending on what you have. So some of those are as follows. You can also calculate just the P part, the real part up here of this complex power, if you know the magnitude of the RMS value of the voltage, the RMS value of the current, and if you take the cosine of the voltage and current phase angle, theta V minus theta I, that's that important angle that's always in all of these equations. So if I have some circuit element here, and I know the